Hello class, welcome to Pre-Algebra Lesson 2-2, which is all about understanding irrational numbers. By the end of this lesson, you should be able to identify a number that is irrational. So let's talk briefly about our different types of numbers, okay? So we have this Venn diagram of sorts. I know you guys are used to Venn diagrams where it's two circles and they overlap a little bit. This is a different kind. But it works the same way. Any overlap means that it occurs in all of those categories that it overlaps with. Okay, so we have this Venn diagram shows the relationship among rational numbers. So the last chapter that we did was all about integers first and then rational numbers, right? We split it into two parts. First part integers, second part rational numbers. Okay, and so along with those, we very, very briefly, I believe, excuse me, I think I only mentioned it maybe in one lesson and kind of in passing, mentioning natural numbers and whole numbers. So something to know, natural numbers are, like if you're ever playing, I think of like when I was a kid and I would play games with friends or something, whether it was like hide and go seek or tag, where you would give people a head start and you would agree upon like, I'm going to count to 20 and then come find you. When you'd start counting, you would start at 1, 2, 3, 4, and you would keep going, right, all the way to whatever number you agreed on. Those are the natural numbers. Those are what you naturally start counting with when you are a kid. Then you learn about the idea of zero a little bit later, and since you're so young, usually when you get introduced to the number zero, you usually don't remember differentiating between it. But the way I think of it is zero being part of whole numbers, that comes after like what you would count, right? So natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, keep going, no decimals or anything. Whole numbers, the same exact thing, except it includes the number 0. And then you can also see that they list some other whole numbers, like 6.0 is still considered a whole number even though it has a decimal. The reason excuse me, this is a whole number is because technically you don't have to write 0.0. You could get rid of that decimal and it would be the same exact number. That's why this is still considered a whole number. And same thing goes down here where I have this fraction, 13 over 1, still a whole number because technically I don't have to write any number as a fraction over 1. So those are still examples of whole numbers. Then the next category is integers. So integers include all of the whole numbers, all of the natural numbers, but it also includes the negative version of those numbers. Okay, so again, no decimals, positives and negatives, all numbers. Okay, then rational are basically, excuse me, all of those numbers in between. Okay, so if a number is a decimal, like 0.75 listed here, that's considered rational because it is terminating. Remember we talked about a terminating decimal is a decimal that ends. Another example of a rational number would be a repeating decimal. So like what we worked with yesterday, converting repeating decimals to fractions, those are rational numbers because they are repeating. Okay, so in order to be rational for a decimal, it has to be repeating or terminating. And then if you have a fraction, that is another form of a rational number because it can be divided out into a decimal, or often you will hear people say, if you can write it as a fraction, it's a rational number, okay? Which is mostly true. Once you get to Algebra 1 next year, I'll show you a couple of examples of when it's not true. Okay, so these are all examples of rational numbers. Now notice we have how would you classify the number 0.24758326, and you can see there are the 3 dots to indicate that it keeps going. Well, those 3 dots tell me that it's not terminating, and I don't see a pattern. I don't see anything that's repeating. There's no bar notation. I don't see a pattern within these numbers. So this number doesn't fit in any of these categories. So this is where we introduce something new called irrational numbers. So irrational numbers are all of those numbers that are decimals that keep going on forever and ever without repeating. So you can see I have this example right here, and then the number pi. And then you might notice a couple of square roots. And those square roots, if you were to type those into a calculator, you would get numbers that keep going on and don't end. There's no pattern. Okay? And if it ends on your calculator, it's because your calculator can only show you so many digits. So you want to look mainly for a pattern. Okay, so now let's practice categorizing rational versus irrational. So we talked about how pi, that's a number that keeps going, the decimal never ends, and it doesn't repeat. So that is a form of irrational. Negative 17, well, that number does not have a decimal, so that's going to be rational. Then I see a few other options here, and by a few I mean actually there are 4 options. I want you to take a look at these 4 numbers and see if you can figure out which category would they go in. Good luck. Okay, hopefully you ended up categorizing them like this, where you said 3.275, that decimal ended, so it's rational, and 0.76 repeating, that is rational because it is repeating. And then our other 2 numbers are going to be forms of irrational because there are, excuse me, there are the dots to indicate that they keep going forever, and it's not the same values repeating. Sometimes I'll have students see, like, they'll see this pattern. They'll say, oh, well, it goes 5, 6, and then 5, 5, 6, and then 5, 5, 5, 6, and they will try to argue that since there's a pattern there, it is a form of rational. So then my comment back to them is, if you cannot write it with bar notation, so what we learned about and have practiced a couple of different times, if you can't write it with this, it's not going to be a repeating decimal. So hopefully that helps clarify that common misconception. All right, let's move on to example 2. Example 2, we're going to talk about square roots. So if we were to try to classify the number, the square root of 3, if you were to type the square root of 3 into a calculator, you would get 1.7320500808, and then it looks like it's starting to get a pattern, but it doesn't. So this would be a form of irrational numbers. Now you might be thinking to yourself, oh my gosh, is she going to let us start using calculators now? You might be getting really excited that that day has come. I am sorry to squash your dreams. That day has not come, because I'm going to teach you how to tell, at least the square roots that we're going to work with for now, I'm going to teach you how to tell if they are rational or not without needing a calculator. So to talk about square roots, let's look at these diagrams here. So a square is this image right here, right? So you can see this square is a 1 by 1, and it covers 1 square. So that's like saying 1 squared is 1. Okay, then over here, you can see that this is 2 units by 2 units, and it covers a total of 4 squares. This one is 3 by 3 and covers 9 squares. So what this tells you is that if you have the square root of any of these numbers, it's going to work out nicely, because that square root just tells you that you're looking for what is that side length. So the square root of 9 is 3. The square root of 4 is 2. the square root of 1 is 1. So all of those square roots are actually going to be classified as rational. Okay, and let's quickly jot down a few more of those perfect squares. So we have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared. Then we'll do 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, and 15 squared. Okay, so 1 squared, 1 times 1 is 1. I'll do this in a different color. So if you ever have the square root of 1, that's going to be rational. So then 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is going to be 225. Okay, so I just gave you quite a big list, right? Like we went all the way up to 225. If you ever see a square root that matches one of the ones that I just wrote, those are all going to be rational. But if you see anything like square root of 2 or square root of 3, so those numbers in between, so square root of 5, 6, 7, 8, okay, and you can see that there's more and more in between each one, right? All of these ones in orange, these are going to be examples of irrational numbers, okay? So if you see square roots that are going to be these orange numbers, which would be in between those rational square roots, those numbers in between are going to be irrational. So that's a really good thing to jot down. And I would say try to know, maybe up to 10. Make sure you know those. But we'll keep practicing with that. Now let's try another categorizing. So I have negative 81,572. Right away, I see there is not a decimal right there. That is going to be rational. And then I see 5.63, 633, 6333. I see that there's a pattern, but I wouldn't be able to write it with bar notation to show that it's repeating. So that's going to be irrational. Now, I have to think which of those is rational, if any. So I'm going to go back and look. Square root of 16 I see is the same as 4 squared, so that is rational. And then if I were to go back and look for 11, I see that 11 is in between my 3 squared and 4 squared. That tells me that that is irrational. And that would be all that I have to do to classify those. Okay, so that is really everything for today. Hopefully that makes sense. If not, please ask questions. I'm happy to help you. But otherwise, I hope you have a great day.